Okay, ladies and gentlemen, this is study 2 of AP Statistics course, and we're going to continue working with sampling and sample design. And I just wanted to make certain I covered a couple of issues and make certain everyone's aware of them. First of all, if you have a TI calculator, this is great. This is the one that's online. We will be using it, and I'll use it in examples and talk about it. As a matter of fact, why don't we take a census right at the moment? Yes, I'm going to try to get all of you to do this for me. I want you to send me a K-mail and tell me if you have a true TI calculator or if you're going to use the simulated one that I have out there in the document sharing. You're welcome to tell me either one. Tell me if it's a TI-83 or a TI-84 and what you're going to be using. Now, the reason I'm saying TI-83 or 84, there are certain things that are different about them, and when we get into the statistics, we need to make certain we're understanding what those are. So, if you can make certain you tell me which one you're using, I would appreciate it. Sip of coffee, and we'll get started here. Boy, that was hot. Okay, let's get started on this. First of all, we're going to be producing data, samples, and looking at experiments and things like that. And this is out of Unit 4, so I want to make certain I'm covering a couple of things. When we're designing samples, well, let's just look at an example here. It says, suppose the principal is interested in finding out if TXVA students think more trees should be planted. He makes an announcement and instructs students to K-mail him to let him know if tree planting is an issue they support. Will this sample of students give him an accurate picture of all the students' feelings at TXVA? Well, I'm supposed to stop here and get opinions from you guys. But since I'm doing this as a recording, opinions kind of vary here a little bit. But the point is, I was asking for volunteers. I was asking for people to give me their opinions, right? And when you ask for a voluntary response like that, the sample consists of people who want to volunteer, people who do support that opinion. They're going to give it to you right away. Therefore, you've already affected the results. And what we call that is that voluntary response samples seem to overrepresent people that have strong opinions. Now, people who have strong opinions the other way would also respond to it. But the whole point there is you're going to get strong opinions on either side, and people that are kind of, I don't care, aren't going to respond. Well, that's one of the things that we call a confounding variable. So unless you design your experiments very carefully, the effects of these variables can make your results be very, very weird. And it's called a confounding variable when that occurs. Okay? So what we're looking for is samples that provide an answer to specific questions from the data with some guarantee the answers are good answers. Okay? This is called statistical inference. And it can be very accurate, and it's a method of collecting, but it can also be very inaccurate if the method of collecting data is flawed. So we have to be very careful about how we're collecting that data. Okay? So let's look at some important terms. We've already talked about population and sample design. We've talked about a convenience sample, and I just did a little bit here about voluntary responses. Bias. Do you think some people are biased one way or another? Well, sure. Everyone has a bias about some things. I particularly have a bias towards Oreo cookies. I don't like uh, plain sugar cookies. I like Oreo cookies. It's a bias I have. I have no problems admitting it. Okay? We all have a bias in some things. Okay? A poorly designed systematic favors certain outcomes or results. That's what a bias will do to you. If you don't design your experiments or your surveys very well, you sometimes introduce bias into it, either your own or the people that you're surveying or the people that you're doing the experiment on. Okay? So let's look at some other cautions here. Suppose we did a very solid statistical random sample in a survey. What lurking variables could confound results? Remember what lurking variables are again? Those are things that affect both aspects of it, right? Well, if we did a survey We might get undercoverage, or we might get non-responses from people. We might get bias from people who are responding to the survey. Depending upon the wording of the questions, we might get some confusion. Okay? So we have to be very, very careful about what we're putting out there in surveys. Okay? And that's just some cautions that you have to be careful about. Okay? So, how do we make an inference about the entire population from just a sample of it? Okay, sample results don't necessarily match population results. We've seen that. I mean, we could say 4 out of 5 dentists believe this way, and it's really 30 out of 50. Okay, that's not quite the same, is it? Well, results could be different. I mean, we know that if we flip a coin, it's got a 50-50% chance of landing on heads and 50% chance landing on tails. But you know that if you flip a coin 10 times, you might get 5 heads and 5 tails. You might get 3 heads and 7 tails. You might get 7 heads and 3 tails. It differs at different situations, right? Well, same thing's true about any of the surveys or anything that we do. Results can change from sample to sample, but since we deliberately use randomity, the results tend to obey the probability laws, which allow for fairly consistent results, with a little bit of fudge factor in there, a little bit of margin of error. Okay? The degree of accuracy can be increased by increasing the size of the sample. Obviously, bigger sample, longer time. Smaller sample, shorter time. So, depending upon how quickly you need the results, you might increase the size of the sample and get better results from doing that. Better in the sense more accurate. Okay? So, when we're designing experiments, things we need to look at. We need to do an observational study. We need to do an experiment. We need to have experimental units and subjects. We need a treatment, a specific condition that we're going to try to do. We have factors, variables of interest that we need to be considering. We have the level, the measure of a particular factor, and explanatory versus a response variable. Okay? These are things that we will take into consideration when we're designing experiments. Okay, here's a discussion thing here. Julie obtains a list of all the seniors in her high school who did not study a foreign language. When she compares her scores on a standard test of English reading and grammar given to all seniors, the average score of the students who studied a foreign language is much higher than the average score of those who did not. So the question is, does this study give evidence that studying another language builds skill in English? Well, let's think about that for a second. She didn't do this herself. I mean, she's using existing students who are in her school and existing tests, the standard test of English written, reading, and writing. It might have been like the STAR test results here, right? Or the TAKS test results. And she's looking at the average score of the students who studied a foreign language is higher than those who did not. Does it give evidence that studying another language builds skill in English? Point for discussion. Why don't we bring that up in our class Connect, and we'll talk about it there, okay? Now, one of the things I want to make certain to cover are the 3 principles of design. And one of the first basic principles of design is to have a control group. A control group is that group of people that you don't change anything on, so that you see that their results stay consistently the same. So a control of the effects affects the lurking variables. That way, you're not getting them to be any different. You're not causing those to be any different. So if they were causing a problem to the original population, the control group, they would be causing a problem to your experimental group too. So, what you're saying here is that without comparison of treatments, results can produce systematic favoritism or bias towards one outcome. And that's what we're trying to eliminate right there. Okay? Having a control group will help us see if there is favoritism or bias one way or another. Okay. Randomized comparative experiments. The goal of an experiment is to collect good evidence for a cause and effect relationship. If I randomize the variables, I have a better chance of hitting that standard and being completely thing, because everything will be equalized and spread out. Okay? Anything that might have been a bias one way or the other has an equal chance of being in one or another of an side of an experiment. Okay? Here, an example. A baby food producer claims that her product is superior to that of her leading competitor in babies gaining weight faster with her product. As an experiment, 30 healthy babies are randomly selected. For 2 months, 15 are fed her product and 15 are fed the competitor's product. Each baby's weight gain in ounces was recorded. Now I want you to notice they randomly selected and then they randomly assigned 15 are fed one and 15 are fed another. They randomly selected 15 healthy babies. These 15 healthy babies might have voluntarily come in one way or another. But if we randomly divide them up into the two groups, we have a fair comparison of the two things. So what they're doing, they're saying a random allocation here. They're dividing the groups up into two babies, 15 babies here and 15 here. One are going to get one treatment, her product. Another are going to get the other treatment, their competitors, or what they were normally getting. And then they'll compare the weight gain at the end. Okay? So how do we get that randomization, that random allocation? Notice down here where it says babies will be numbered from 1 to 30. Using a random number table, the first 15 numbers selected will be in group 1 and the remaining placed in group 2. That little statement right there tells you how it was randomly allocated. Okay? That is one of the aspects of a AP test. You see this diagram here and here? This is called a randomized design. If you were asked to create a randomized design for a product, you would be expected to draw a table similar to this and have a statement very similar to this in your answer. So what are you saying, Mr. Green? I'm saying that when you see problems that ask you to do experimental design, this is what we're looking for. You're going to see a couple of these when we go through, and we'll talk about this more when we go into our Class Connect. But this is what they're looking for as an answer, okay? Because they want to see how you're putting it together. You've got a randomized allocation, you've got two different groups that are created, two different treatments, one for each group, and a comparison of their weight. Okay? Here, another one. So, another example. If we wish to determine whether or not a new type of fertilizer is more effective than the type we currently use, researchers subdivided a 20-acre farm into 20 one-acre plots. Wheat will be planted on the farm. At the end of the growing season, the number of bushels harvested will be measured. Produce a diagram for the experiment. Well, we got 20 acres here. What we're going to do is we're going to randomly allocate the 1-acre plots from 1 to 20 using a random number table. So we'll go through there and we'll say, well, here's the first plot. Look in the random number table, pick a number, give it to that one. Here's the next plot. Pick a number on the random number table, give it to that one. They go through and number all 20 of the plots with different numbers. They'll take the 10 lowest numbers, and that will be group 1, and they'll take the 10 highest numbers, and that'll be group 2. Why did we do that? Well, we're trying to eliminate other variables from affecting it. What other variables could there be? Wind. Maybe the wind coming from one direction on the field affects the growth one way or another. By randomly selecting that side of the field and selecting whether they'll be in group 1 or group 2, you eliminated that variable because you will have some in one and some in the other group. Maybe water has a factor to do with it, and just by subdividing the land into 20 different places, randomly allocating them out allows you to eliminate water as an effect here, because it is, even though it might not be equal to all 20 of the different lot plots, it will at least be randomized, and at least some of them will get good water, and some of them might get a little bit less, some of them might get a little bit more. Okay? And then the bushels of wheat will be, from each plot, will be counted and compared. So we'll be able to see, was it treatment 1 or was it treatment 2? What was treatment 1? It was the new fertilizer. Treatment 2 was the current fertilizer. So what is the current? The current is the control. And the new treatment is this one up here. Do you see how this diagram is showing you all that information along with this paragraph down here? So, statistics on the AP test. Do they have questions like this? Yes, they do. You will be given a question like this. Every test for the past 10 years has had a experimental design question on it. Okay? Now, experimental design doesn't stop there. Okay? Let's see here. I have talked about, let's see here. I haven't talked about randomization. Randomization produces groups of experimental units that would be similar in all respects before the treatments are applied. The comparative design ensures that the influence of the other experimental treatments operate equally on all groups. Therefore, differences are due to the imposed treatment or the play of chance on the random assignment. Okay? An observed effect so large that it would rarely occur by chance is called a statistically significant change effect. So experiments with many subjects are better able to detect differences among the effects of the treatment than similar experiments with fewer subjects. So having said that, bigger experiments, better results. Okay. So the three things that we were talking about, the principles of experimental design: control. Having a control group is important. Randomization, the use of impersonal chance of assignment to specific treatments. And replication of the experiment on many subjects to produce a chance variation in the results. This is size, randomly assigned, and control. Control, random, and replication. CRR. Those are the things that you need to make certain you have in any experimental design you do. Okay? So, the success of an experiment depends upon the ability to treat all the experimental units identically except for the actual treatment. Some people refer to this as a double-blind experiment. The most serious potential weakness of experiments is lack of realism. The setting of an experiment may not realistically duplicate the conditions we want to study. So you have to be really careful with those type of things. So I'm giving you all these cautions just to be aware of. Okay, one more topic here: block design. A block is a group of experimental units or subjects that are known before the experiment to be similar in one way that is expected to affect the response of the treatments. A matched pair is when each subject in the experiment will receive 2 and only 2 treatments. The order is randomly selected to preserve the important aspect of randomization. Let me talk about the second one first, the matched pair design. What if we were to compare 2 different types of brownie recipes? We make the brownies exactly according to the plan. We cut up the brownies so that there's no crust on them, and we eliminate every other possibility of things. But then we take our subjects and we divide them into 2 groups. And we give one, when we randomly assign them out into their 2 groups, they get to taste both brownies. But the order that they're tasting the brownies differs. So one might taste A first and the other one tastes B first. The other one might taste B first and then A first. And you ask them to rate the brownies and then compare them, which one they liked most. That's called a matched pair design. You see how there were 2 treatments. Each subject got to do both treatments, but by random selection, they didn't know which one they were doing first and which one they were doing second. This is the Coke versus Pepsi experiment that you see them do, where they're randomly tasting Coke and Pepsi to see which one they like better. Or comparing 2 things together, and they're giving them one and giving them the other one, and they try them both, and they make a decision which one they like best. Block design, like I was talking about here, is trying to eliminate things that we know are going to affect an experiment before we get started. Let me give you an example. If you are participating in the design of a medical experiment to investigate whether a calcium supplement in a diet will reduce the blood pressure of middle-aged men, preliminary work suggests that calcium may be effective and have an effect and that the effect may be greater for African American men than for white men. We can tell right there. There's a difference. There is a variable that we might not understand affecting this design. So we want to eliminate that variable. So what do we do in that? We call it a block design. We're going to not only divide them amongst African American and white men, but then we'll randomly assign the African Americans, one into group 1, one into group 2. One will get the calcium treatment, one will get a placebo. And the white men into group 1 and group 2, one will get a calcium treatment, one will get a placebo. And then we'll compare the blood pressure at the end. Not only will we be able to tell if calcium is better than the placebo in African American men and in white men, but then we could compare the African American men versus the white men to see if there was a difference between the calcium treatments and see if it did have more effect with them. Okay? Now, I used a term in doing this block design called a placebo. What is a placebo? A placebo is not the real drug. It would still be giving them something, but it would not be the drug that we're trying to treat, that we're testing as a treatment. Okay? It would just be another type of inert object that would not affect what we were looking at, their blood pressure. Okay? Having said that, that's what we talk about when we talk about a block design. See how much more complicated this is than just a regular random sample? This has been one of the ones that has been on the test recently, is this block design. There are others, and we will talk about them at a future time. But I want to make certain that you understand what we're talking about here is that we wanted to get certain aspects of this design put together. Now, in your practice, you're going to be practicing with different types of block designs and with different random samplings. Play with it a little bit, see what you come up with, and get back with me. I'll be looking for you at Class Connect, and we can talk more about it there. Now, don't forget, if you're trying to send me a K-mail, make certain you tell me you're in the AP Stat class. If you don't tell me you're in AP Stat, I go looking all through all my courses, and I got 8 or 9 different courses that I'm having to look through, and it might take me a while to get back to you and answer your question. But if you tell me I'm in AP Stat and here's my question, I get right to it and I can find you and I can answer your questions real quickly. Okay? Okay. Well, I look for you in the Class Connect on Thursday morning. Bye.